Hello again. Tonight's topic is stop looking for small, start looking for big. And small as in microbes, and big as in things much bigger than microscopic. Yeah, there are scientific efforts to look for extraterrestrial life, and they're running into issues. When they look for things at the microscopic level, either living or fossilized dead things, they'll go out and they'll capture some pristine material from an asteroid or a comet tail, and they'll bring it back to Earth in supposedly a biologically isolated environment, and then they'll find either living or dead bacteria on it. And they'll say, well, that can't be from space, obviously, must be contamination from here on Earth. Well, forget about that. Now, how you would recognize it as being space-borne bacteria, not quite sure. That space bacteria is going to be different than Earth bacteria. Remember the scientific adage of everywhere we look in the universe, everything is the same. When we look at physics, it's the same as it is on Earth. When we look out in space, it's the same physics, the same chemistry, the same spectroscopic analysis of elements and compounds, and atoms seem to work the same way. Photons seem to work the same way. So if you did actually capture something at the microscopic level, how would you say that it's going to look different than out there? And, they would say things like, well, if we sample chemistry, we find that the isotopes of hydrogen that are dominant on Earth are different than the isotopes of hydrogen that we should find out in space. That's a presumption. If it's out in space itself, yes. But if it's out on something terrestrial, like an asteroid in space, or we find it through a spectroscopic analysis of the atmosphere of some exoplanet, that should not look any different than it does on Earth. And so whenever they find, hey, it looks just like it does here on Earth, must be from Earth, or must not be what we're looking at. It's realistic explanations of what they're saying, but then I'm giving them the benefit of the doubt. And it's more like, maybe you're saying that because you don't want what you found to be what you actually found. So there's definitely life here on Earth. Obviously, we're an example of that life, a sophisticated example, but there are also other examples of life on this planet that are existing just fine, surviving in environments that humans would find we wouldn't survive for very long without protective suits or enclosures like submarines or pressurized compartments or something. And those forms of life are called extremophiles. But we haven't even found any extremophiles coming in, from outer space or anything. So, but we discount most of the extremophiles because, well, they're not sentient because they're not talking to us. That's our enormous bias for anything on this planet that doesn't communicate with us. Obviously, it's not sentient. Well, that's like saying because somebody speaks another language, they can't be possibly as smart as you. That's just not meaningful. Or because extremophiles are thought of as being generally small, shrimp, little lobsters, things like that, maybe some small fish sizes. But what you don't see are the extremophiles they find in very deep ocean water, not around the volcanic vents, but hundreds of feet above them, suspended in the water, are very large tentacle creatures that the individual tentacles are how they collect their food. They collect things out of the water. Those seem to be quite large, but they're very frail. None of these extremophiles exist well in our environment. So as soon as you take them from cold, deep, acidic, base waters into our normal environment, they're not going to live for very long. So that's, we discount them because they're hardy, but not that hardy. Okay, how hardy are you if we put you down at a volcanic vent? So there are two general branches of where stuff came from. One is it all came from right here, and it came from raw material. We didn't need any help from elsewhere. That's called abiogenesis. That's one branch. The other branch is, well, the planet was pretty much sterile. We might have had some chemicals, but, it came from out there, accidentally landed here, and then took off. And that's called panspermia. Or even more unacceptable to most people is it was purposefully brought here. The planet was pristine and, brought primitive life here and then add a few millions to billions of years and helping it along as you see fit. And that's where we came from. No proof of it, but there are people that believe. Personally, I'm agnostic to any combination of the above. It could be abiogenesis. It could be combined with panspermia. It could be from assistance from others out there. Doesn't really matter. I just know that there's a lot of life here and it has abundance and diversity. But are we creating an unrealistically high hurdle for when we find something out there? Now, if we do find something out there and it gets corroborated, peer-reviewed, confirmed, concluded, there's life out there in whatever form, if it's just bacteria or if it's creatures roaming around or if it's intelligent creatures that, oh, there they are, and we talk to them. Doesn't matter. It's going to be sociologically transformative. A lot of people will freak. A lot of people will have to rewrite some stuff. But, it's a giant cliff, a giant hurdle that once you cross it, there's no going back, so to speak. So we have to come up with a skepticism of whatever evidence we see that will say we're not going to cross that hurdle easily. We're not going to conclude there is, and then, well, 10 years later we find out, oh, we were just fooling ourselves. Really isn't. When we get something in, like let's say we have a sample from a pristine asteroid or comet tail, we bring it back into a lab that's as clean as we can do it, and then since the organisms come in from the deep cold of space, and the first thing we want to do is examine them, we kind of have to heat up the chamber to make it where, like, humans can stick their hands in gloves and not make their hands into icicle popsicles. So we have to warm up the chamber a bit. And then the next thing we do is we start shining bright lights on it so we can see what's going on. We look at it not with, scanning electron microscopes initially, but with just optical microscopes just to see what's there. And then when we want to get the smallest stuff, bacteria level or virus level, now we're going to start hitting them with X-rays because we want to use electron microscope to scan it. So if anything, we're alive in space and needed that environment, much like the exophiles on the bottom of the ocean floor needed their environment. And then we subjected them to heating and then bright lights and then X-rays. If anything survived, it's going to be an extremophile, because if it was a normal biological kind of life that we find here on Earth, we just killed it through heating and X-ray and bright lights and all that kinds of stuff. So the only thing we would be able to determine existed, if ever, is extremophile in space. If we're looking for particles of certain elements or chemistries, compounds in the atmosphere of, let's say, Venus, or in the atmosphere of some exoplanet orbiting a star, then when we do the spectroscopic analysis and we say, well, we found that it's 23 parts per million of phosgene. Okay, so that could have been naturally created. Okay, how do you get and sustain 23 parts per million of phosgene without some recurring source that you can't identify? Well, here on Earth, we find that, at 3 parts per million, it's naturally occurring. Okay, you just said low number and you observed a high number. How do you go from the natural geologic process, low number, to get to the high number that you're now discounting? Spectroscopic analysis is easy to kick to the curb, so to speak. But if you have that unrealistically high burden of proof, under what scenario would it be possible for you to say, we found something, we've peer-reviewed it, we've confirmed it, it's irrefutable, we have a conclusion, there's life elsewhere? I think what they're doing is they're not trying hard enough, and they're creating hurdles that, what's the old description that Carl Sagan was tagged with? Unbelievable stuff requires unbelievable evidence. So maybe we should flip it around somewhat, and instead of looking for the small, let's look for the big and obvious that's irrefutable. So we can still look for the microscopic stuff. We can still, do spectroscopic analysis, but much like putting a camera on the Juno craft allowed us to see other things than the instruments that went on board could see, and we saw new data. We saw interesting stuff. Maybe we should do the same thing when we send spacecraft out to look at I don't know, a moon of Jupiter or a moon of Saturn. Maybe we should equip it with all the normal stuff, the microbial, the spectroscopic, but let's equip it with some of the stuff that we use here on Earth. When we put satellites in orbit and we want to do stuff here on Earth, let's look for more obvious stuff, bigger stuff. Let's look for maybe larger forms of life than microscopic, maybe structures or infrastructure that we can't see by looking at tiny stuff. We have to look at bigger stuff. So how do we go about doing that? There are people that will doubt it and say that, maybe extremophiles exist elsewhere. And despite all the vastness and commonality we see out in space, there's, as you remember from the movie Contact, there's nothing out there but noble gases, dust, dead rocks, frozen, salty, irradiated subsurface oceans. There's nothing out there. Don't waste your time with that SETI work. Well, I don't see it as being wasted time. I see it as we're just maybe looking and using the wrong instruments and such. If you're only looking for microbes, then you're not looking for anything bigger. If you're only looking for gases, you're not looking for anything bigger. I'd say continue to look for your small stuff, but let's start looking at the larger stuff, just like we do on Earth. And then once we find it, kind of harder to deny that. So on Earth, we have instruments in orbiting satellites that do agricultural analysis. They do insect movements. They watch animals in the oceans. They watch population herd movements. And they do all this from space. They find settlements. They find cities beneath forests and buried beneath sands in desert areas on the Earth. So why aren't we sending any of those kinds of instruments out to examine like Mars or Venus or moons of other planets? Well, we are sending those instruments, just not the same kind. So when we send instruments out there, we're not looking for stuff the size of a person or structures that a person might use. We're looking for other things. We're looking for bigger stuff. When we send radar to a satellite to orbit Mars, we're not looking for small stuff. We're looking for terrain. We're looking for potential landing sites, mountain ranges, valleys, big stuff, and not moving stuff, stationary stuff. And we have yet to actually scan below the surface of things, except on Venus. We did point radar at Venus, and we looked through the clouds of Venus, and we could see the terrain. But the resolution of that set of images was good enough for a flyby, so we can see valleys and mountains and stuff. But the resolution was nowhere near what we even use here on Earth. So finding smaller stuff just wasn't in the cards. But when we do that on Earth, we can find, leftover historical sites on Earth that are buried beneath the sands in the Middle East. Send those kinds of instruments out there. So look for larger things. I have a scale reference here. Let's say we wanted to find an ore or multiple ores of multiple rowboats, rather than looking for one aircraft supercarrier. So I want something that has enough resolution where I can go, that looks like the oar of a rowboat, meter size, not hundreds of meters. Because if it's hundreds of meters, it's hard for me to make out anything small. But if I have the resolution where I can spot something the size of an oar and make out that it's an oar, not that I'm looking for oars, just this is an example of the resolution, then if we spotted something, that would be meaningful. Here's the difference between staring and scanning. If I send a probe to Mars, like the Mars Reconnaissance Orbiter, and I equip it with a camera, and it orbits, and it tilts its orbit, and it does strip scanning, and it covers the entire planet, the resolution it's looking at is hundreds of meters per pixel. It's looking for terrain. It's not going to be seeing anything smaller. It just isn't. Well, when they're scanning, you won't see anything that's moving if it's moving slowly. So if you scan over an area and you have some living object that is moving at, let's say, a tortoise pace, you're going to scan it once. It's just going to be a small dot. You won't have the resolution to see it, and you're never coming back that way again. Or if you do come back that way again, it might not be there anymore because, it's been a month or a year since you were there the last time. So you need to move from scanning quickly to staring for a prolonged period of time. And we do that here on Earth. So if we want to look at a particular site, we have a geostationary orbiting satellite, and it stares at a particular area at high resolution. And that's how we see things, that are small and below the surface. That's how we can, how do we spot swarms of locusts moving across areas where, hey, heads up, the locusts are headed your way. We spot the swarm. We don't spot the individual locusts. Same sort of thing. Or as we do with near-Earth asteroids, we do what is known as blink comparison. We take a picture, and then we come back not too long afterwards, take another picture of exactly the same spot, same field of view, same magnification, same illumination, and go, did anything change? If you remember that movie with Val Kilmer, Red Planet, the creatures that ate some of them, you didn't notice them initially because they weren't moving. And then when you kind of looked away and then looked back, they had moved. And it wasn't until they got close enough that they just started coming at you. Well, maybe things do that. And the other thing you need is a dynamic region of interest. This is where if you're in orbit and you're stationary looking at a spot and you see something that you'd like to investigate further, you don't keep the same field of view. You don't keep the same magnification. You zoom in on that small item. So you get the maximum resolution over the smallest area. And that's how you look at things that might be even smaller than a meter in size. So now you can see like maybe a tortoise moving kind of thing. But until you have adjustable dynamic region of interest and magnification and scaling down to very small levels, you can send instruments to Mars all the time looking for terrain, and you're just not going to spot any of this stuff. Now, these sorts of instruments that we put in orbit around the Earth, this is how we look for industrial sites and military sites and pollution sources. And when we put things up in geostationary orbit, and we can put them at different places, that's how we find these things. So in summary, we've been looking for small evidence, microbes and spectroscopic lines. We need to start looking for larger things, larger forms of life that might be moving, larger structures or infrastructures that if you're looking at it from a very low magnification, high field of view, you may not even notice them because they're individual things, like a wall or a corner of a building that's left over after millions of years. You won't even notice it. Or if it's covered in dirt, it may be below the surface, and you have to use, Lidar or radar to penetrate the surface to see it. Now, when we go to one of the moons of Jupiter and Saturn that have deep oceans underneath a crust of ice, we are going to be using radar and maybe even submarines, small submarines, not human crewed submarines, but robotic submarines, to go below the surface and use radar to see below the surface, much as we did for Venus. I just hope that we send ones with high enough resolution that we can see smaller things. So once we have repeated peer-reviewed evidence using these new kinds of instruments, it'll be far easier to confirm and conclude and far more challenging to refute whatever evidence we find. Though some will still try, but the conclusion is simply unacceptable to them, however we want to state it. Not only would be not considered alone in the universe, but also maybe not even that unique if we find it at multiple places. And, here's the ego blow. Maybe we're just not that interesting after all, but we won't know until we see. And I added another acronym for a membership here for Planetary Society. There's a hyperlink there that if you get the PDF in the email, you can link it. So back into the 1970s, the ongoing mystery of the Viking life detections, just a walkthrough of all the different analysis they did to prove or disprove it. Videos about, did we find microbial life on an asteroid? This is from Hayabusa. coming back to Earth? Did we find signs of life in the atmosphere of Venus? Did we find a marker of life in the atmosphere of an exoplanet? And then for those people that aren't familiar with it, abiogenesis and panspermia. And then if you want to know about the kind of stuff that we currently put in orbit and what its resolution is that we aren't sending to deep space, synthetic aperture radar, microwave radar that we have orbiting the Earth right now can see to a 1 meter resolution. How do you track a herd of buffalo? Well, you need a SAR radar that can see a swarm of buffalo and see the herd moving. Other thing is LIDAR, the laser kind of radar, usually works in infrared. It has a 70 centimeter resolution. Now, obviously, when it's scanning large areas, it's just looking for big features. And then when it spots something, it can narrow the beam down and get down to a resolution of 70 centimeters. So if you want to look for a turtle, you can find a turtle with that kind of LIDAR. A smaller turtle, like a little box turtle, 70 centimeters. So put the right instruments out there and maybe you'll find what you're looking for. Put the wrong instruments out there and you'll never find what you're looking for. Okay. Comments or questions? Is it just me that thinks we're putting the wrong instruments out there to maybe not find what we think we're looking for? Because, I mean, the instruments we have in Earth orbit right now are far higher resolution and more capable of zooming down to a spot than what we send to other planets.
So therefore, you're recommending that we change our attitude?
Well, I would recommend we change our attitude on the kinds of instruments that we put on deep spacecraft so that they're higher resolution and are not just, strip scanning wide areas for terrain. They can actually go, hey, I just found something. Let me tighten up and look right there. And let me continue looking right there. Because what I'm looking at, if it moves, I want to know that. Yeah. If I only come by every month or every year and look at it, I might not see it because it's passing through. Or if it doesn't pass through, it's not high enough resolution for me to see it, even if it's just sitting there. And if it's not penetrating, if it's synthetic aperture radar and it's of the wrong wavelength so it doesn't penetrate dirt and rock, we'll never see something that's below the surface, like those early civilized sites that we find in the Middle East that are buried beneath 100 feet of Arabian sand. But we can see that now because we have the right instruments in orbit. Let's send the right instruments elsewhere.
Yeah, that's right.
Yeah, that's the whole idea is let's stop looking where the light's bad and let's start looking where the light's good.
Well, it's hard to believe that we don't. Well, I mean, when they sent back pictures of Mars, the first one, and Curiosity was rolling around, they were taking pictures all over the place there. And it looked like if in fact there was a road there, we would see that, or somebody walked by, we would see that. I didn't realize that what I hear you saying, sort of, I don't know for sure, is that we're not actually using a camera that would tell if somebody walked by.
No, what I'm saying is the area on Mars covered by Spirit, Opportunity, Perseverance, and Curiosity is smaller than New Hampshire.
Okay.
If you were comparing that. So if you said, I'm going to land a spacecraft out in the middle of the Mojave Desert, out in New Mexico, and I'm only going to allow it to go about 5 miles in each direction. I can remember being out in that part of the country and driving for 2+ hours at high speed just to not see dirt and rocks anymore. Now, luckily, I was driving on an asphalt road, but if I was in a rover and I only drove for 30 minutes, I would never see anything but dirt and rocks. I need to be able to look over an area and go, I found something of interest, and then I need to zoom in on it. And you're not going to do that with a rover that can't go that far.
Well, when we sent Curiosity, we didn't know if Curiosity would work, right?
Well, remember, Curiosity was not the first of its kind. We had a very small rover that we didn't think was going to last for very long, and it lasted for, I think, 200 days. And then we sent Spirit and Opportunity, and then we sent Curiosity, and then we sent Perseverance, and we sent the Ingenuity helicopter. And the
Whatever happened to that helicopter?
It went.
Did it die?
It didn't die. It went over an area of ground that was mostly sand, no rocks that were perceived by the cameras, and so its automatic navigation system got confused, and it thought it was flying level when it was actually flying at a slight angle, and it came in to land, and it didn't land flat. It landed kind of on the side, and the propeller got whacked by the sand at high speed, and the end of the propeller broke off. All the electronics are still working. The motors are still working. In fact, they did an attempt to take off again and found very quickly it was not stable. And so, okay, not flying anywhere, but occasionally Ingenuity will talk to Perseverance just to see the electronics. So the solar panels are working, the electronics are working, the radio is working. The bottom facing camera that's currently sitting, 4 inches above the ground is still working, but not taking pictures of anything. So it's still there. And someday when humans wind up on Mars, they may go visit and go, oh, poor thing. Here, let me take you into the lab and fix your propeller.
Yeah. Now, they were trying to look at bigger things with that. I mean, by putting a helicopter there on the planet.
No, because it never got very high.
Yeah, but I mean, wasn't that the goal of it, though, to see something different than what we were seeing?
No, the idea of Ingenuity was twofold. The first and foremost was, can we, as a technology, create an aerodynamic vehicle that will operate in the thin atmosphere of Mars? So the helicopter itself. And the second thing was, hey, we can get it to fly on Mars. Why don't we use it to go a little bit ahead of where the Perseverance rover is planning on going and see if we can use it as a terrain scout ahead.
Yeah.
And since it was only going about 100 feet off the ground and it was going relatively slowly, it could see how far Perseverance is going to go tomorrow. It can see it the day before. And that's as far as it went. So it wasn't looking over a large area. It wasn't like flying at 1,000 feet. If you've ever looked at the Ingenuity helicopter, you'll see that it's specifically designed for the low pressure atmosphere on Mars. It's very tiny. It's really tiny. And the propellers are very large and they unfurled. And there's 2 propellers on the same coaxial spindle. So they counter rotate. So you don't need a tail rudder.
And they're spinning like crazy.
Yeah, they're spinning at very high speed in order to get enough lift in the very thin atmosphere. So a normal drone on Earth wouldn't even be able to get off the ground on Mars. Thin atmosphere.
Unless they were redesigned.
Well,
I think there should be redesigned as a drone type, but just it would have to be lighter and aerodynamic to be lifted up. But I mean, it still could be on the principle of a drone, right?
Helicopter more so than a drone.
Oh, really?
Yeah. But what they did come away with it was there's enough air on Mars, not for people to breathe, but for a wing of a certain size to aerodynamically hold an aircraft aloft. A helicopter hovering is not very efficient at using its energy. A glider is. So if you can create a propeller-driven glider, it will probably be able to go a lot farther. And the wing area is a lot larger surface for solar panels than is the couple of square panels that Ingenuity had. So instead of building a future helicopter or drones, they're looking at building future electric sailplanes to go to.
Okay. And are these sailplanes going to accomplish what you're thinking of as a larger picture of it?
No, but the one thing that I did see was kind of a part of their mission was they want to be able to put a relay station at the edge of Valley Marineris, like the Grand Canyon of Mars, put one right on the edge as a radio relay station, and then fly the sailplane down into the bottom of the canyon. Supposedly, the bottom of the canyon has enough differential pressure and temperature that instead of it being dry down there, it's actually slushy, salty ice water. And if that's the case, that would be something that would be worth investigating. And if you could fly a sailplane with, let's say, a 4K camera down to within, 40 feet off the surface of that liquid and something were moving in the water, you could see it. But if you're flying above the canyon, you're 1,000 meters away from the bottom of the canyon and you won't see it.
Okay. I can see that would be a hard, but I still think that aren't we getting pictures? I mean, if there was a building on Mars,
yeah,
when you're saying we wouldn't know that because we didn't put any special detectors on it, or like on the moon, we wouldn't have noticed. When we had people up on the moon, I'm not sure what.
No, what I'm saying is, if there were ancient sites on Mars or on the moon, and they were millions of years old, they may be in even worse shape than those civilized sites that we found buried beneath the sands in the Middle East. You couldn't see them from the surface. They're just sand and rock.
Right. Right. And I understand something underneath. Yeah. Underneath the surface. I understand that we haven't tried that, but we haven't had that technology on Earth for that long either, have we? I mean, I wasn't aware of it for 20 years.
We've had synthetic aperture radar looking at the Earth for about 20 years.
Yeah, 20 years.
Lidar, we've had maybe 8 to 10 years.
Okay, so we're developing it here, and yeah, I would think that would be our next step, would be to go out there on planet. But I mean, if there were buildings and roads and streets and people walking around, we would know that on these planets.
You would think so.
Yeah, I would think so.
Made, but if you were to send a probe to fly over, as I said, the desert Southwest, and you happen to find an area that's 500 miles across that's nothing but dirt, rock, and no civilized cities, you would conclude the whole planet has no life on it. You would have to scan the whole thing. You wouldn't
do that. You wouldn't conclude that.
It's unacceptable because we haven't looked everywhere we can look.
Right. And the thing is that I thought that when they go out and they scout these places where they're going to be landing, I didn't know that it was limited to a certain area for them to look at.
Oh yeah, yeah. We're only looking in certain places. We take very long distance images of areas on Mars, and then we go look in just those areas. And the only thing we're looking for is terrain. Is it mountainous? Is it jagged peaks? Is it flat desert plateau? And we'll go for the flat desert plateau because it's easier and safer to land $1 billion spacecraft there than it is to try and land it in an area of jagged peaks. So
true. But yeah, I imagine that, I'm not sure, but I thought, because we do have like models of these, of say Mars. Yes. I've seen the models of Mars where they have the whole surface all the way around the whole planet, yes, where they tell you where there's dips and peaks, and they've named different places on Mars as to what I don't know why they named them certain things, but they named different areas, certain areas. And I thought it was because we were aware of that surface being, level or up or down or mountainous or, whatever there. I never imagined that we focused on a certain area, such as you say, like if they went to a place anywhere that there's a desert for miles and miles on Earth, and just assume that the rest of the planet was like that. I couldn't imagine that that's what we've done. I still, that
The
does
full,
it, mind boggles me.
the full scanning of Mars was from orbit, and it was looking at a resolution that was about 1,000 meters, about a kilometer. So if you're looking at an area and it shows that these 4 pixels all look like they're the color of dirt, it's a large, flat, sandy area to land. If these 4 pixels look like dark or differentiated light and dark, then that's probably jagged. But when you put all that together, you have a globe of Mars. Now, what's the resolution of each pixel on that globe of Mars? It's about a kilometer. So are you going to see smaller things? Absolutely not.
Okay, so when you say that, I'm
Mhm.
trying to get this in my mind.
Yep.
You're saying it's a kilometer. So I would be, if I was in the desert here on Earth, then that would be normal. Then I would just see a flat land. But if I was in New York City,
Yeah.
where they have all the buildings,
Yes.
would that look like mountainous area because it's all, jagged, or would it? They wouldn't know what it was. We would not know by looking at that picture. We would just know that it wasn't flat.
You're assuming that the buildings are contemporary. If the buildings happen to be 1,000,000 years old and they've gone through a lot of Martian windstorms and seasons and winters, the buildings may not look like buildings anymore. They may just look like rock formations.
But my question is that they look like the building, like New York, then they would. I'm saying don't say that it changed. Say it is a building, and it looks like a building if you could see it today. Is my camera not able to tell that because it's so far away?
No, your camera can tell that. But if the only place where there's life on Mars is down at the bottom of Valley Marineris, we have no imagery.
True.
No
I can
imagery.
understand that.
Yeah.
I was just saying on the surface, we have technology that can tell us if somebody's walking out there.
Yes.
Okay, all right. I was thinking that maybe we're too far away to be able to see things because that's been a problem.
It has actually been a problem because remember at one time from Earth-based telescopes, there were canals on Mars.
Right.
And then we sent the first Viking pass by, flyby, and they realized quickly there's no canals on Mars. And then when we sent the next Mariner to orbit Mars, it's like, yeah, there's no canals on Mars. But there are canals on Mars.
Right.
At the bottom of Valley Marineris, by way of spectroscopic analysis on a sunny day on Mars, we learned that there is liquid salty water at the bottom of the valley.
Right. I knew. Yeah.
So
aren't you also assuming that
water on Mars, not up on the high level of the surface, because the solar wind tends to strip off the water molecules, but down below there is. So did we see it? No, we thought we saw canals, but we didn't see canals like we see on Earth. We just saw light and dark areas of rock, and we thought, oh, Mars is bone dry. There's no water on Mars. And then as we started to look better with better instruments, we found, oh, wait a minute, there is salty water way down in the bottom of the Valley Marineris, and we've never been down there and we don't have any photographs of it. But we do have spectral analysis of it. So, yeah, whenever the proclamation is that doesn't exist or there is nothing there, there's nothing to see there, keep looking.
Yeah, are you not also assuming that another civilization would have made buildings and roads?
Maybe 1,000,000 years ago.
Well, maybe they have another way of living and they don't make buildings.
Maybe they're underground.
Yeah, or something like that.
On Earth, over towards the Middle East, there are underground cities that you can't do anything above the surface except rock and dirt.
Yeah.
and you can go in there, and the underground complexes could easily hold thousands of thousands of
Yeah.
citizens for a long period of time.
And you would never see that from the surface.
You'd never see those from space. You'd never see it on the surface. It would just look like rock and dirt.
Okay.
So if
So we had this, you're saying that it exists today,
yes,
but they don't have people down there.
they have tourists down there.
Oh, just tourists. So I see.
Yeah.
Those are the worst kind of civilization.
It was discovered. They went back and looked at the materials, the pottery shards and stuff, and they found about when it was occupied. And they said, well, there was thousands of people underground living, and then after a time, they came back up to the surface. So maybe they realized due to some event, life on the surface was no longer habitable, and they lived underground. Or to defend themselves from a warring nation, they went underground and blocked everything off. And eventually, when things got better, or they poked their nose outside and didn't get it cut off, they came back to the surface. But these places exist. They exist in the US, they exist over in the Middle East. That's just, historical, physical things you can go see. The ones in China are the most massive, though. There's just giant caverns with enormous pillars holding up the stone roofs. And, it just goes on for a long ways underground. It's not a spotty little site. So how many people lived underground starting when for how long? Don't know. But if you're on Mars, on the surface, things are still not habitable by humans. And therefore, if they have to live, maybe they're living underground right now. But until we scan below the surface, we're never going to know.
And they never come up to look at the little toys on their surface, eh?
No, because
surveillance cameras they have.
We cannot live on the surface of Mars. Radiation, temperature, low pressure atmosphere, maybe they're close enough in biology to us that they also can't live on the surface. So they're underground. Keep looking. Use different instruments. Don't stay focused on just we're looking for bacteria or we're looking for spectroscopic, otherwise we're not looking at all. Yeah. Look, keep looking that way, but look elsewhere too.
It doesn't sound like it's easy though, because I'm thinking, oh, you could just send up a drone, get a collection of drones and send them out. But you're saying, oh, well, it's not going to be easy to look for large things. And it sounds like it would be easy because they would be
right
there.
It should be relatively easy because we already have that technology of sensors in Earth orbit. So it should be relatively easy to just reapply the technology we already have in Earth orbit to be in Martian orbit or to be in Enceladus orbit. Okay. Anything else before I stop recording? Hearing nothing?